Alright, here we're starting week 8, and this is about the hydraulics. Alright, pressure compensation components of the TMS. So we're still into the TMS and tether management system. So that's the submarine base for the ROV. Just a recap. Okay. I got a squeaky chair, which we don't like. Okay, so nearly all submersible systems operating today utilize oil-filled housings when the interior components will not be damaged. When the interior components will not be damaged or affected by oil submergence. The reason for using oil-filled housings is to keep water out of housings that have walls too thin to withstand the crushing pressure of the deep ocean environment. All right, so we see the pressure 1 atmosphere cans, right, with like the inch out of the milled aluminum with the inch thick walls. So now this is for thinner wall, okay? Since water and oil are practically incompressible, there is no change in volume inside oil-filled housings unless there's air inside. Hence the air and water checks, okay? The importance of them. The benefits are being able to use thin wall materials at much less cost and having much higher payloads as a result. So that's self-explanatory. The lighter that the ROV is, right, with these thin walled housings, the more payload it can carry, okay? The drawback of using oil-filled housings is that Boyle's law and Charles' law must now be taken into account in order to compensate for the behavior of gas, which is air in the deep ocean. So Boyle's law states for any gas at a constant temperature, the volume of the gas will vary inversely with the pressure. In other words, the higher the pressure, the smaller the volume. And conversely, the lower the pressure, the larger the volume. For example, assume that the temperature remains the same. Let's say the volume in the balloon at the surface is 10 liters. Now, if the balloon is submerged, the equivalent of 1 atmosphere, right, 33 feet, 10 meters, the pressure outside the balloon will be doubled and the volume inside the balloon will be halved. Surface pressure equals 14.7 psi and volume 10 liters. At 10 meters, pressure is 29.4 psi and the volume is halved to 5 liters. Alright, so do you get that? 14.7 and volume is 10. 10 meters down, it doubles and the volume is halved to 5 liters. Return the balloon to the surface and the gas volume will expand back to 10 liters. Charles' law states for any gas at a constant pressure, the volume of the gas will vary directly with absolute temperature. In other words, the higher the temperature, the greater the volume, and conversely, the lower the temperature, smaller the volume. For example, if a housing was submerged to a depth of 10 meters and the trapped air inside was then heated up by the operation of a servo valve, the volume of air would expand directly with the increase in temperature. Conversely, the volume would decrease as the housing cooled. So now we have the TMS and ROV, oil-filled housing and hoses being submerged in the deep ocean. Two methods are used to compensate for the external pressure acting on these housing and hoses. Oil-filled pressure balanced. This method is used for subsea cabling when the cables are filled with oil but not pressurized, meaning the oil inside is pressure balanced with the ambient pressure outside. Oil-filled pressure balanced. Pressure compensated, again. This method is used for housing in some hoses that have a positive pressure applied to them by use of a spring-biased accumulator, meaning the oil inside is at a higher pressure than the water pressure outside, which should keep water out. So know those two and know the difference. So here we got a compensator, right? Some people would know it as an accumulator probably. Those with a hydraulic background. And that being said, if you have a hydraulic background, you are light years ahead of people, alright? So hydraulics is good to know. The positive pressure is achieved by use of a compensator, which is an oil-filled variable volume spring-loaded device used to maintain an above ambient pressure in the circuit and the housings connected directly to the compensator. Here's an example of pressure compensated tog-on hose and MSAL, metal shell aluminum, bulkhead connector, and whip end connector, compensated because it is under positive pressure from a spring bias compensated bladder. As most of the whips on a TMS and ROV are specialized as the number of wires, shields, etc. needed for the devices they control, it is advantageous to be able to make up our own to specific lengths and to be able to replace them quickly if damaged or deteriorated. So I already talked about the importance of, and how cheap yet effective these tog-on hoses are, putting in your own wires, and to get them through like 6 to 10 foot lengths. Say you got like 6 to 8 wires, right, or even 10. The best way to do it is to fish them through, is to sort of make these a twist in these, like braid it. So to braid it, you would put one end in a drill and the other end in a vise. And you would do what I call the Jesse James method. So Jesse James is this guy that was into motorcycles, making his own motorcycles years ago. Not the outlaw Jesse James, okay, from the 1800s. And you do, a control speed and you twist your cabling. Now, knowing that if you take off the drill and or let go of the vise, it's all going to come unraveled, right? So you'd have to like sort of tie wrap it into place. But now you got a nice braid made. Have this tog on, like if you're out on a ship or a rig. Have it tied to like a ladder that's built onto the frame or something vertical that you can get up on. Put a little lead weight, tie a little lead weight on the tog on the wires, and with a bit of string. Drop it through from the top, and then when it comes out, pull through the wires, right? You got your 4 to 6 inches on each end that you can then solder your wires together. Shove in this end, clamp it, fill it up with all, let it burp, right? Get all the air out of it, and then do the other end. Okay, makes sense? Hopefully. Tog on and stainless steel band clamps make it cheap and easy. Alright, so I just said all that. An ROV housing is oil filled and pressurized is said to be pressure compensating, meaning the pressure inside the housing is higher than the ambient pressure outside. This method is used when the components inside the housing will not be affected by pressure variation or immersion in hydraulic oil. The housing is filled with oil to a prescribed positive pressure setting, usually between 2 to 15 psi. The compensator provides a small volume of oil to make up for small leaks and trapped air in the circuit. These individual comps, as they are commonly called, are each monitored either electronically through the telemetry system or with physical pressure gauges, or both. The compensator also acts as expansion chamber that permits changes in oil volume caused by temperature variations. If a housing is subject to excess heat generation, such as a servo can, the pressure will be kept low as the oil volume will expand. Each housing has its own separate air bleed and water check ports. The air bleed ports are located at the top, as air bubbles will migrate to the highest part of the housing, and the water check ports are located at the bottom of the housing, as water is heavier than oil and will sink to the bottom. Component housing units are usually connected to the compensator with clear plastic Paraflex tubing that is rated between 75 to 250 psi, well above the normal pressure settings on TMS or ROV, but some systems utilize rigid stainless steel tubing. Clear plastic tubing enables air and water bubbles to be detected, so you can see it, right? Like I said, very effective designs. So Paraflex comes in 50 to 100 lengths. So this is in inches here, right? 0.375. That's OD is outer diameter, okay? 0.093. Wall, natural. So here you got 3 Firestone bladders, okay? The respective combination of Paraflex and stainless steel tubing. Alright, so you can see all the tubing, right? You got your pump, your motor, tog on, filled with oil, okay? Air checks up on top, and someone down below Like there's a ball valve for isolation, another ball valve for isolating. Alright, but somewhere there should be a water check there. Not very clear on this picture. Once again, another isolation check valve. Alright, so if you want to drain this can, you would turn this off so you wouldn't drain like more than needed. You had to do maintenance inside of here. Each housing can be isolated from the pressure compensation bladder by a 1/4 turn valve like the one on this transformer housing. This enables individual housings to be drained and open for repair and maintenance without draining down the compensator units and introducing air into the circuits, which will be difficult to remove later. It's very important to ensure during pre-dive checks that all 1/4 turn valves are in the open position, enabling pressure compensation between them. Alright, so this will be with some old supervisors. And there's two trains of thought about this. I'll get back to you there now in a second. So as I was saying, with this ball valve, and some supervisors training new guys, they may have them in the turned off position. So once they tell you to go down, do like a kick the tire check on the equipment before pre-dives, make sure that you always remember this, that they should be in that open position, okay? Now, that is an effective way of teaching. Is it a good way of teaching? I don't know. Yes and no. Right? I know I passed it because I'm aircraft maintenance, but I didn't really agree with that method of trying to be tricked. Alright, but hey, it shows you're doing your job, right? When you do catch stuff like that, right? So there you go. Normally, water checks are done by drawing a volume from the compensator and from the housing to get a sample of the oil inside. This will flush any accumulated water out through the bottom of the housing and the compensator until only clear oil is flowing. Air checks are done by connecting to the top of the housings. These housing connections are normally made with quick disconnect QDs. Alright, so remember that term. Units that allow rapid connection between the housing and the drain and fill containers used by the technicians. Alright, so this is the male end and female end. Okay, and that's what they're called from the hydraulic industry. Okay, so this, got to make a little clicking noise as it inserts into this. If it doesn't make the clicking noise, then it's not going to work. Okay, so remember that for the rest of your life. Most pressures have remote access panels for easier checking and filling of the compensators. Normally all pressure adjustments are made through the compensators, not at the housings they're designed to protect. This ensures that any water in the circuit will remain at the lowest point, which is normally the compensator unit. Alright, so, they should have these little banks made, shaft seals, valve packs, right? Port motor, starboard motor, it should be, left to right. Okay, and that being said, fill up your housings through the compensators, like what it says, right? And just these rulers are just here to give you an idea of how big everything is, okay? So the low pressure in these compensators and housing is monitored by a simple glycerin-filled 15 to 30 psi pressure gauge mounted in an easily viewed location somewhere near the TMS pan and tilt camera. So there's a pan and tilt camera that can tilt down to the bottom of this tether drum, left, right, and up. And you would have to do this, right? You would have to monitor your gauges during the dive. Any changes in pressure can be noted during frequent comp checks. That's what I just said, okay? And everything's here labeled, okay? Which it should be. Some of these pressure compensated housings have the potential to become overpressurized due to a failure of an internal hydraulic fixture or seal, normally a high pressure system valve or solenoid. If high pressure or hydraulic oil from the main hydraulic system leaks into a sealed circuit pressure tubing compensated housing, it can quickly rupture the housing or tubing and create a crisis situation. 20 psi check valves are used in these housings to reduce the risk of overpressurizing the circuits. So I've come across this, right? We're thinking we'll get into it later. A solenoid inside of a pressurized housing has an O-ring missing. So the system pressure when we start up this ROV XL38 is leaking into the static side. And there's a blow-off valve there that's coming out through a blow-off valve. So that requires a draining, right? Isolate, drain, make sure the power is off to begin with, lockout, tag out, and check the solenoids underneath. So that's, 4 screws, take them off, but it's not as easy as I'm saying. It's in a hard to reach spot, but it's got to be done, and it will be done. So this is what I'm talking about. These are rate control valves, right? Solenoids. Possibly cause pressure hydraulic oil in the housing, causing overpressurize of the comm circuit. So this is exactly what I'm talking about. On the back side of these, right? So 1, 2, 3, 4. Right? You'd have to drain this can down, make sure all the power was off beforehand, right? 1, 2, 3, 4 screws, haul it out and check to see if the O-ring is on the back side. Check valve permits a one-way flow of oil away from the housing, but only when the pressure exceeds the setting of the check valve, which is normally about 20 psi. If a leak should develop and pressure builds up, the check valve is designed to release this pressure either back to the main hydraulic system reservoir or vent it directly into the sea. It should be noted, however, that these valves can handle only about 1.5 gallon per minute of flow, and any higher flow rates can quickly overpressurize the housing, possibly causing a failure. These failures are rare, however, and can usually be anticipated, noticing a trend developing in the affected housing by careful monitoring of the compensator gauges before, during, and after dives. Pressure gauge changes unexpectedly or trends one way or another. It's time to troubleshoot. So clean all systems such as valve packs are normally routed to the main reservoir. Contaminated housings like thruster shaft seal comps, which are frequently contaminated with seawater due to the intake of water through the thruster seals, are simply vented into the sea. Some of the housings on TMS that require pressure compensations include termination pod, a slip ring assembly as they are connected, transformer pod, rate valve pack, servo proportional valve packs that thrusters are installed, thruster shaft seal adapter housing, mounted in series, electric motors, vehicle, HPU reservoir domains, hydraulic power unit. Let's see here. The hydraulic oil is used in the pressure compensation system is the same oil as that used in the TMS and ROV electro-hydraulic system. The main reason is that the hydraulic oil from the static comp may mix with the main hydraulic oil should an overpressure situation occur. If dissimilar oils were used, the above scenario would necessitate complete draining and flushing of the main hydraulic system. A more practical reason to use the same oil for both system hydraulics and compensator hydraulics is that you only have to stock one type of oil in bulk, and since the main hydraulic oil system oil is already approved for subsea use and is suitable for static comp use, why not use it? Alright, so electric motors now used on the TMS and ROV, and are especially designed to run at higher voltages in a subsea environment. So you don't run these on deck, okay? Not for too long anyway, they're water cooled. They're similar to standard industrial three-phase electric squirrel motors, but have thinner housings to reduce weight and are not designed to operate out of the subsea environment due to their susceptibility to heat damage. They are designed to be immersed in water for cooling and are not designed to be run on the surface. Cannot be stressed enough that these specialty motors are also not designed for multiple and frequent start-stop cycles. Alright, so don't go turn them on and off like that. Electric motor will draw a very high amperage due to starting the startup, which results in excess heat generation. The motor winding installation can sustain cumulative permanent damage resulting from overheating due to excessive running time on deck or from multiple and frequent start-stop cycles while on deck. So here is a green colored, right, anodized again. Now with this, right, they're fairly heavy. All right. So usually get the crane crew or something. If you got to change out one, get the crane to lift it. If not too strong people, can put like a pry bar or something in between that lift eye and carry it themselves, taking frequent breaks. Okay, so I've had to lift it up several decks one time with another guy. Not the easiest task. The motor usually has its own dedicated compensator unit to prevent the accidental ingress of water from another housing. Here you can see the electric motor connected to the hydraulic pump alongside several Firestone comp units. Alright, so this is the same old picture. So electric motor flow again, the TMS units typically have only one electric motor, with a wide range of power ratings depending on the system design and hydraulic load. Now, however, the power requirements is usually the same as the ROV in order to have similar components and spare parts, etc. Motor is one of the simplest components on the TMS and is remotely started and stopped from the PDU and runs quite independent of the rest of the TMS electrical components. These electric motors typically operate at about 1800 RPM, revolutions per minute, okay? Spare motors, electric motors should be stored boxed up full of oil to prevent corrosion damage, being careful not to damage the exterior anodized coating. With proper care and preparation, motors and other components can be stored safe for years and be ready for service immediately. So the electric motor's only job is to turn the hydraulic pump, which provides a hydraulic flow to turn hydraulic motors and extend and retract hydraulic actuators. So there's your pump, there's your motor, okay? This is on XL38 by the looks of it. So note the spiral wrap on hydraulic hoses, right, for the chafing against the steel frame. Alright, so all that helps, right? Used a lot on aircraft, obviously. Right, but even a place where there's an edge, you can use a thing called caterpillar too, okay? You glue it on the edges. It's like a sort of a round, it makes it a rounded plastic edge then. Both would be better, but this will do. Snakeskin is another one, okay? I always remember that for wire harnesses and hydraulic hoses around steel. And what else here? The hydraulic pump is typically a variable displacement, pressure compensated axial piston design. Axial piston pumps convert rotary motion provided by the electric motor to an axial reciprocating motion. As the pistons move into the cylinders, they draw oil in and expel it under pressure. They are called variable displacement pumps because they will supply oil at whatever rate is demanded by the system up to the pump's output capacity. For example, if the pump is running and there is no demand for oil, it will de-stroke itself and only supply enough oil to make up for internal leakage up to the maximum pressure setting. This reduces heat generation and extends the life of the pump. Right, so de-stroke. So HAWE, hydraulic, you can put that in, right? So there's a little definition and you can go on, right? Flow rate, on stroke time gets into it. Different types of pumps here. That being said, now here's another one. Types of hydraulic pumps with detailed explanation. We'll just let it run for a second.
An external gear pump uses two gears rotating against each other
to
provide fluid movement. One gear is driven by a motor connected to a shaft. This is called the drive gear because it is driven by a motor, and it in turn meshes with and drives the movement of the second gear. As the gears rotate away from each other and come out of
another one. Hydraulic pumps explained. Axial.
Hi guys, welcome back to howmachineworks.com.
How an axial flow variable displacement pump
Today
works.
Let's learn how an axial flow variable displacement piston pump works.
So they're all
with the help
good.
Of this
you
animation.
can go on and
so
on
please
and
watch
on.
the entire animation and learn it. First, let's identify the components. Here, this is the casing of the.
There's another one. Alright, hydraulics and pneumatics. And this is pretty good too. So like as you're reading or listening, always email me if you're unclear, but take it upon yourself to go the extra step, extra mile, and search for the truth yourself, okay? And you can go on and on and on. Like I say, the ROV course, especially if you get some experience at it, you can get jobs at various other sub-trades, we'll call it, okay? Okay, like in a hydraulic shop, right? In an electronics store, you know, with a windmill farm. As a repair and maintenance technician with Baker Hughes or M.I. Swaco or Schlumberger, Halliburton, Franks. You know, I'm just thinking oil companies. There's, you know, defense companies, right? As long as you get electromechanical experience, and this course trains you on both, and that's all I can say. We'll go back to this. These pumps are designed to operate at a fixed RPM, and the pressure outputs can be adjusted to suit the hydraulic system they are powering. They have a control module that permits adjustment of two pressure settings, maximum pressure and bypass pressure. The DR setting will be set at the highest setting permissible on the TMS ROV system, normally about 3000 psi. And the FR setting will be a lower value, usually called the bypass setting, around 650 psi for starting the motor pump and for reduced power requirements. So remember now what we said about the amperage and all that earlier, right? So it's all tied in, even though we're talking about hydraulics and PSI now. So FR, right, for the starting, and DR is the pressure setting, and the FR is the flow. So here you go. This is how two spools that can be adjusted with Allen keys. So there's a little printed procedure for this. So right here, DR sets the maximum pressure and FR sets the bypass pressure. Okay, so right here, you get your wrench. You take off these caps. Then this is exposed, okay? So you got to loosen this lock nut, and then with the Allen key, clockwise, right, would reduce the orifice as far as I can remember, and what I've done in the several times I've done this procedure, thus increasing the pressure. Counterclockwise, you opens up the pipe, the river, whatever, alright, and the pressure decreases. Once you set it to whatever setting you want, or your supervisor tells you, or the manual says, hold it tight with your Allen key and use your wrench to lock it into place with your lock nut. Right, you cannot move this spool with the Allen key when this lock nut is tight. This got to be loosened off at first. So that being said, when you go to loosen this, put your Allen key in to hold this steady so you know what setting you had it on, okay? Makes sense. 28cc pump moves 28 cc's or cubic centimeters, which is a milliliter, okay? Per revolution at 1800 RPM. 50,400 cc's, 13.3 gallons per minute. Therefore, a 28cc pump can produce a maximum flow rate of 13.3 gallons per minute to supply actuators, thrusters, and motors. Know this, a hydraulic pump does not pump pressure, it creates flow. Pressure is the result of resistance to flow. Alright, high pressure, low flow rates, low pressure, high flow rates. High pressure equals low flow rates. Right, makes sense. Going back to this, right, what I said here, right, you decrease the orifice, right, decreasing your flow rate in the river, the pipe, right, just think on water and all that, you got high pressure. So I'll give you several sites to visit about the hydraulic pumps, and you can, your homework is to look at those videos and sites. The reciprocating motion draws fluid and during one half the rotation and pumps it out in the other half the rotation. The change of angle of the swash plate increases the volume of oil drawn in the cylinder from the output side, which results in increased volume of oil being expended on the output port. Let's just see if this one opens up.
So Lit Mobile just sent me this solar wireless battery pack. I'm excited. Let's see what's inside. I really like
Alright, so, like I say, he gets a clue. He's spinning. That being said now, like with most of these parts, like you will have time to fix it, but a lot of times, like, time's money offshore. So you're gonna like isolate, take this pump off, put on a new pump or the spare pump, and start it up and see if it works, okay? Then on your downtime, you will take this apart and self-teach yourself / repair, okay? Sometimes you won't be able to repair it. A lot of times you will not be able to repair. And any component that has a tamper-proof seal, and how can I explain this now? Tamper-proof seal would be a sticker from the manufacturer. Just say this part could come off, alright, even though I know it can't. You had a sticker right here that, done this little step. If the sent this back to the manufacturer and they see that this seal was broke, they would void your warranty, okay? And you will be held responsible because you got into something you weren't supposed to. Okay, so heed my advice on tamper-proof seals. We'll talk about that later with cameras and all that. I'll give you a story, but right now we're dealing with hydraulics. So most hydraulic pumps use subsea on the TMS and RV only have 2 pressure settings, maximum and D-stroke, commonly referred to as bypass. Full system pressure is the maximum pressure that a specific hydraulic system is designed to operate within, alright, about 3000 psi. Bypass is a reduced setting that is selected when starting the electric motors in order to reduce the load on the motor and pump and therefore reduce the startup amperage and resulting heat generated in the process, 650 psi, and to prevent a locked rotor condition on startup. So the main things to know about ROV system hydraulic pumps are they have a fixed operating pressure and they can supply a variable volume of oil to the system based upon system demand. Remember that. Now here we are, the mains, okay? The main compensator. Alright, joint, firestone bladder. Now this is just on the Magnums and Millenniums, right? Not all ROV systems got this style. So the main reservoir, usually called the mains, is exactly the same kind of pressure compensator used to pressure balance static housings, only larger, includes temperature and volume sensors. The mains reservoir volume of oil, hydraulic oil, is dictated by the flow requirements of the pumps and the components they supply. Now I don't like this configuration here they got. Alright. This is outside, more or less. Well, I just don't like the way that's wound up, even though it's inside this cage frame. I just, obviously they got too long, right? This is what I'm talking about, right? They use 10 feet for, looks like a 6-foot runner. You know what I mean? No need. Okay? That's just a problem. Really, it is a problem. Especially with these white tar wraps, they're the worst of all the tar wraps. They become pretty brittle over time and crack. Alright? So just be aware of little things like that, right? Cut things to the length, at least enough for 3 services. So if we say you got 6 inches, a foot and a half. So if this was a 6-foot run, 7.5 feet would be long enough. Alright, and I don't mean 6 feet in a straight line, You use a string or a rope and fake run it. Take the rope in the shop, measure what you got, and add another 1.5 feet, okay? Then you're safe. The hydraulic pump must have oil in order to supply all the downstream motors and actuators with flow and pressure. The mains comp usually only holds about 20 to 30 liters of hydraulic oil. The mains is spring load to maintain a maximum head pressure of no more than 7 psi on the fluid in order to prevent cavitation within the pump resulting from a vacuum condition and to keep the system pressure compensated. Comp pressures greater than 7 psi can also cause damage to the pump by the mechanical action of the piston shoes lifting off the swash plate and violently crashing down. This is another reason never to run the electric motors on deck because there is not a large reservoir of oil to provide cooling and the pumps will rapidly overheat, which can lead to seal failure and premature pump failure. Alright, so this is an important page, okay? And we got the mains hydraulic reservoir is also fitted with a linear motion transducer to measure oil volume. This is usually just a running plate on top of the comp with a hole in it that moves up and down around a fixed linear transducer bar that senses a change in the running plate's position. You can see this on the left side of the mains comp in the pictures 2 pages earlier. It's also a sensor to monitor the hydraulic oil temperature. Signals from both of these sensors are processed by an analog board in the electronics pod to be transmitted to the pilot's computer to the displayed on the pilot monitor and connected to a low oil alarm system. Right, so remember we talked about the analog cards, right? This varies, so it's analog. Linear motion transducer, left side of the pump, right? So that's it here. Alright, and as it moves, as it expands or contracts, right, this slides up and down this bar. Okay? And like I say, feel free to get in the linear transducers, motion transducers, all you want. You're going to be taught it anyway, I think, with another instructor. So now we have an electric motor turning a hydraulic pump which provides 12.5 gallons per minute, 3000 psi hydraulic oil supply to the TMS hydraulic system. Hydraulic fluid is pumped through the system in fluid conductors of hydraulic hoses and stainless steel tubing. Steel tubing is not used as susceptible to rust and corrosion, and painting will just conceal damage that could lead to component failure or serious injury. No fittings or pressure components are ever to be painted. Alright, so that's like, you know, a cardinal rule. Stainless steel, a cardinal rule. Right, do not use plain steel. Safety factor 4 to 1 is the minimum recommended on the pressure rating of the hydraulic plumbing material. So the working pressure of the hose or tubing is determined by dividing the rated burst pressure by the safety factor of 4. So a tube with a burst pressure of 12,000 psi can safely handle a 3,000 psi working load. Stainless steel tubing, SS, is used for its anti-corrosion properties, unlike steel tubing, and is easy to assemble and attach fittings onto. Stainless steel tubing is used when rigid lines are required. Stainless steel tubing is very durable and, if installed correctly and properly maintained, has a very long working lifespan. Tubing is measured and specified by its wall thickness and the outside diameter. Pressure ratings are based on tubing rating and wall thickness. So most fittings I've used, not the pipe now, are 1/8. So you measure outside to outside. Okay, quick way of doing it. And subtract a quarter, because you got 1/8 on one side, 1/8 on the other side, right? 1/8 plus 1/8 is 1/4, and you got your size of pipe, or size of fitting, I should say. Okay. Now that's a quick way. It doesn't cover everything, but it's, you know, a field technician way of doing stuff. Okay. Often tube is pre-flared to 37 degrees, so accept a 37 degree flare connector. Alright, so you can see the flaring, right? Okay. And one piece of tubing is joined to another tube connector or component with a tube connector and fastening nut. These connections and fittings are easy to assemble and require no welding to achieve leak-free connections if quality materials and proper installation techniques are used. So this is like the manufacturer will go by, because we used to go by the catalogs out there. This is like a swage lock. Alright, so you can see, like, you know, what do we got? 1, 2, 3, 4, 5, 6, 7, 8 or 9 threads, thin walled, right? And it screws in like that. Looks like probably a pipe thread on the other side. So we could get that for you. So here's some, you know, I just put in swage lock. Well, you can put in swage lock, JIC, pipe thread, MPT, alright, national pipe thread, MPTT, national pipe thread, tapered. Alright, so here's like common fittings you'd have offshore, okay? So there's a T, alright, there's an O-ring boss. See the O-ring on it? Unmistakable, obviously, right? JIC, okay, pipe thread on the other side, right, pipe up here. Alright, so you'd have to know these. These would be in separate drawers, like when we done the work van earlier, in week 2 or something like that. So each you'd be swage lock in one drawer, JIC in another, right, like a number 2 fitting, a number 4 fitting, number 6 fitting, whatever. Actually, I don't even know if there is a number 2 fitting anymore. Number 4 anyway, right? number 6, number 8, stuff like that. So familiarize yourself with this. So when someone tells you to go in, even though it's labeled, you know exactly what to go for. Alright, there's a swage lock there with a pipe thread on this side swage here. So like I say, right, you get some experience, you can get a job at worst case scenario. Times get tough at an electronic shop or a hydraulic shop. Right, because everything is cyclic. The oil industry is cyclic if you're getting into that. If you're going to use ROVs for the oil, and some people won't be, but that was my background, and it was like the aircraft industry. Every 5 or 6 years, right, it's a boom or bust. So hydraulic hoses is used in application where lines must flex or bend, such as a moving clamp actuator. Different types and amounts of reinforcement give those hoses specific pressure ratings. Hoses can last a long time, but all rubber slowly deteriorates with contact from various substances such as solvents, water, sunlight, heat, ozone, etc. Hoses are not as permanent as stainless steel conductors and should be replaced when damaged or past their estimated useful life cycle. Most companies use a hose register to keep track of each and every hydraulic hose used throughout the surface and subsurface units and place them at specified intervals of time, usually every 3 to 5 years depending on company policy. Alright, so preventative maintenance, replace it before it bursts. Okay, because you don't want a spewing of oil into the environment or on a person, especially at high pressure. So remember that. Alright, preventative maintenance. Example of stainless steel tubing flexible hose used on the ROV. Note the QDs and holes connected to the stainless steel tubing. Alright, quick disconnects. Here they are here. Once again now. Alright. They're a bigger one. It could be a hydraulic lock. Alright. This hose is connected to a torque tool that must be able to move, unlike the yellow thruster which is fixed mounted to the ROV frame and can therefore be plumbed with rigid stainless steel. Alright, so it looks like, I don't know if it's really tight, but this must have been during a journey. You would have ratchet strapped the ROV to the deck, okay? If it's on a ship, when you're going from St. John's out to the Grand Banks, or wherever the destination was. Alright, so that's it for week 8. Any questions, as usual, email me. And use the YouTube. Teach yourself a bit, right? Brush up on hydraulics. You will be doing a hydraulic course and a fluids course with another instructor. So you'll have at least 2 courses. And controls and all that, like the linear transducer and all that, you'll be doing with another instructor. So you got lots to learn yet. This is just an intro course. Alright, over and out.